Boom! Welcome to Mr. Beals AppSlam. The University of Colorado Boulder has put together the PhET interactive simulations. I think these are a very useful set of simulations. There's a wide variety of them. Physics, I like the physics stuff. We're going to look at the black body spectrum, and then we're going to go to heat and thermo, which is sort of chemistry related, and check out one of those. Black body spectrum, when you click on this, brings up a second website. That website looks like this. This is visible light right here, and as you go here you get more and more red. And the black body spectrum, the way it works is you got a lot of intensity shift between that goes with temperature. So if we down here at Earth, this is room temperature. You've got this very low intensity. This is 1 micro megawatt, so it's basically 1 watt per meter squared per micrometer, right? So that's the curve, and this curve goes off like this, with the highest intensity over here, very far into the red. And as we bring the spectrum up, let's go to an oven. You can see it shoots way off. The intensity is logarithmic, so it shoots right past our scale. So that we've got these convenient buttons. We can minus them down and bring the scale back down to something reasonable. And you can see it's still very red, with the peak still off to the right past what we can see. Still red. So let's bring it up towards a light bulb. Bring up the light bulb. Wow, it just shoots right off the mark. So the intensity at UV is higher than you had at the peak back with the oven, with the light bulb. And we can bring that down so that we can look at the curve. And you can see the curve here. We got the peak intensity is in the infrared, but there's plenty of visible. So the light bulb, you can see, and it'll light up a room pretty good. And as you get brighter, as you bring the light bulb, as you get brighter and brighter light bulbs, it'll become more and more like the sun. So you can get more into the visible. And you can see as we pull the sun up to about 6,000 there, 5,700, and bring the intensity down, you can see that the peak here is just at the edge of the green. That's why plants are green, because they want to capture as much as they can right in here of the sun's light. And so that's the black body radiation demonstration. So let's go back and let's go to heat and thermo. And I really like this demonstration, the gas properties one. So if you click on this, it brings up Java. We've already loaded that in. Here it is here. And let me reset this. So you can see there's a little guy here. He'll move in and out, and he changes the volume. You can pump gas in. That puts the gas in there. Let's do some of that. Let's hold, and you can hold different parameters constant. We'll demonstrate that in a second. If we pump in some gas, we can see there's no pressure yet, but as the gas starts to hit the walls, the pressure pulls up, and quickly it goes into equilibrium, where you have the same amount of gas bouncing on the walls from moment to moment, and that's when the pressure stabilizes. We got the temperature here at 300. If we move the little guy in, bring the volume in, it does energy, so it's going to bring the pressure up and the temperature up. Let's watch that happen. Boom, so you see the big wave of gas smashes around, brings the temperature up, the pressure increases, so we've got about 2 atmospheres there. We can do the opposite. We let some of that out. It's a fixed amount of heat, so every little guy that leaves is taking some kinetic energy with him. And there's less molecules to be banging on the wall, so the pressure drops down. Temperature and pressure is back down. We can cool it off directly. That'll further remove the heat, so that when the molecules bounce against the cold wall, they don't bounce back as fast, and so things cool down. Temperature is down, and we can add heat, and you get the opposite effect. So you can see the molecules start bouncing faster, and the heat goes up, and the pressure goes up. We can also do something interesting. We can hold the pressure constant, and this little robot here will then move to adjust the volume to account for small changes and try to keep that right at 1 atmosphere. If we pump in some extra gas, he's going to have to make it a lot bigger to keep the same amount of pressure. So you can see him dancing backwards, trying to bring it back down to 1. So you can help him out with a little bit of ice. Right, the temperature drops, and then we're going to overshoot probably. And now he's going to have to bring it back in, add a little bit of energy, and get it back down to 1. So you can play around. You can hold temperature constant, volume constant. There's a lot of different ways. And I think this is a good opportunity for students to get get the hang of how gas dynamics or whatever the simulation is, get the hang of how the physics works, and get a sense of change this and that changes, and they can visually see it, and they can play around with it and understand it better. I think it could flip the classroom. They could do it at home, and then we could talk about it and do problems related to it at school. You could do it as a demonstration like we did here in the classroom. Ask for student volunteers maybe, or if you have enough resources in the classroom, the students can work in groups and play with it in the class. So I hope you enjoyed my video, and look for the next one.